Okay. Right, I will also see people are joining. I see someone with a very strange. Is that? Oh. One second, I will start shortly. I just want to make sure that uh, there are no intruders in this one, because I just saw something. Okay. So, um, are there any questions about yesterday's lecture? Now, one thing I would say is that from yesterday's experience, that it is, I would prefer if you ask the question by raising your hand rather than writing on the chat box, unless you have any problems like mic is not working and so on, because then otherwise it takes some time to read through the questions. So if you have any questions, you can about the last lecture, then you can ask me now. One thing I missed in the last lecture, I will tell you shortly. The other part is that, so this is a general and probably advice, is that there are many gravitational wave lectures available now. Wait, sorry, I just want to turn on my video. There are many gravitational wave lectures are available online, so you can, and then of course there are references and everything is available. But I think the advantage of a summer school is that you have the chance to interact with people who are doing research. So I would suggest that you take advantage of that more. And anyway, these lectures will be available. I guess this will be available, or there are many other, in fact, better lectures available online for offline or later viewing. So the interaction is probably the most important thing. It is unfortunate that this generally in summer schools and refresher courses, we have the opportunity to have tea time discussions, which is not possible this time. So I guess the lecture period is the only time when you can discuss. Okay, so before we start today's lecture, which will have more importance on the detection, I just want to say one thing which I did not stress in the last lecture, which is about the importance of numerical relativity. So what we should do is, I will just go back a few slides, and then I just want to show you this part. So you remember the animation anyway. So what happens here, if you remember that statement which was made in the as a one-line description of general relativity, that's space-time, that matter tells space-time how to curve, and space-time tells matter how to move. So that can be kind of literally sort of applied here. I mean, of course, it's very crude, but sort of that example gives you an idea of what is going on. So let's say you have a stretched rubber sheet and you put a very heavy mass there at the center, and then you take a small test mass, let's say ball bearing, and you roll it. Then you know that the motion of this small mass will be determined by the curvature of this surface, which was made by the larger mass. So in this case, this larger mass told space-time how to curve, and space-time, which is the geometry of this rubber sheet, told the smaller mass how to move. In practice, however, this is more complicated, because these masses could be of similar, these objects could have similar masses, in which case each one of these would influence how the other, how the curvature changes, hence how the other one moves, and the other one's movement will then dictate how the first one moves. So in some ways, each one of them are going to influence their own motion. So this is basically a non-linear process, and that is why it becomes very difficult to solve Einstein's equation analytically when these bodies are moving extremely fast. Otherwise, when they're far away, then you can probably use some kind of Newtonian approximation, because the energy loss is less. So the frequency change is much less. So it is almost like an elliptical or quasi-circular orbit. But then as they come close, it becomes very difficult to solve it analytically because of this non-linearity of of Einstein's equation. So this is one of the most important reasons why you have to use numerical relativity. Okay, now I will skip all this and go back to the detectors. Okay, one last time, no questions, right? I don't see any hand up and I don't see anything on the chat box, so I'm studying. Now, the first detection of gravitational waves happened through the observation of a binary pulsar. You have heard about this already. It was done by Hulse and Taylor. And in this plot, you can see that these observations were carried out for more than 30 years. And there are these dots which show the exact measurement, and the solid line through it, this thin line which is going through these points, show how the general relativity prediction, and you can see that how beautifully the prediction matches the observation. Of course, this prediction is dependent on how well you know the masses and so on. This is basically what is plotted here is not exactly how the period changes, but how the periastron shifts. That is, the ellipse does not close exactly; it slightly starts moving like this. Instead of closing, the ellipse sort of moves, and that is what was measured here, plotted here. Now, this was still not a direct detection. This is like you have a, let's say, black body. Let's say a hot object, a cup of coffee, and then you know that there are radiation coming out of it, and somebody predicted that this radiation is going to follow Planck's distribution, and if you integrate that, you know that the rate of emission of energy would be proportional to T to the power 4. That is the Stefan-Boltzmann law. Now, so what we have measured is sort of like how the body is cooling, but not exactly the Planck spectrum. Okay, that was happened with the Hulse-Taylor pulsar. So the direct detection would mean to directly detect the gravitational wave, not the effect of the loss of gravitational waves in a system. Nevertheless, this was a very important discovery because it showed that gravitational waves exist, and they got a Nobel Prize. Okay, so now how do we directly detect gravitational waves? This also you have heard in the lecture, just very briefly, that when gravitational waves fall on a ring of particles, it executes a motion like this. It basically gets distorted. The ring of particles would get distorted, keeping the area nearly the same. So now we will actually calculate this, that how we are getting this pattern and so on. So what happens is that if now you put a rod along, let's say, a central line here, let's say here, then the rod is going to fluctuate. Okay, but then that is one way to detect gravitational waves. But a better way would be if we can put an interferometer here, because we are, as you can see here, by looking at these patterns, the gravitational waves is causing differential changes in the length dimensions. So if we can put a Michelson interferometer in this form, then and the Michelson interferometer is very sensitive in the arm length, the difference between the length of this arm versus that arm. So it can measure these fluctuations very accurately. So this is the best way to do it. However, it is much more challenging than that, and we will come to that in a moment. The problem is that these fluctuations are in this picture are highly exaggerated. The actual effect is much smaller. Okay, before we go in there, I just wanted to stop the animation, and I will just show you some of those calculations, how we know that this is going to be the shape. Okay. Okay, let me see if technology works properly. Okay, so I think in the general relativity lecture, you have seen the metric equal to, I don't know which convention was used, but it does not matter. Okay, so let me how do I erase? Come back to the plane, this thing, and now I have to write basically Gij dxi dxj. Okay, so you have seen the general metric. Acha, can somebody confirm that you can see it properly?
Yes, we can see.
Okay, so the general metric you have seen, that I will also write on the somewhere. So, okay, it is not allowing me to write it there. Okay. This is sort of to okay. Now, however, in this G mu nu, which we saw yesterday, that it could be written as eta mu nu plus h mu nu, and this eta mu nu is the standard Minkowski metric. Basically, we can put, and here what we saw yesterday is that in the transverse traceless gauge, we could write this as all zeros. I did not spend too much time explaining what these quantities are, like, you know, the each elements of the this metric and so on, assuming that in the general relativity course you have kind of understood those. Okay, so this is H plus minus H plus and H cross here, H cross. So this is the sort of picture we drew. I showed you the equation that day. So now what we are going to do is that now you can see that basically the time part, that is the 0, 0 part, has no component except one, that is this part. Wait, I have to use the mouse. Only these components, which are x and y. So this row, second row and column basically correspond to x, and the third column and row correspond to y, and z direction is the propagation direction. So there is nothing, no other components there. So if we assume, if we just consider the plus polarization, in the previous one also you saw that, you know, I have to tell that, but just consider the plus polarization for the time being. Then what happens is that there are only two components, H plus in the 2 component, and the minus H plus is the 3 component. Both H plus and H cross are sinusoidal functions, so they have the form of this omega t minus kz sort of form. So then if we substitute, now what we are going to do is that, now let us take this interferometer. Okay, let's say this is the x-axis, this is the y-axis. Okay, and there is a, let's say, mirror here, mirror there. Now consider a light propagating, this is the pinch meter, along this direction and then coming back. Okay, now, okay, in a normal class I would have asked that what do you think, so it would be this d square for light, but I guess that will be too difficult here, but let me write down c square dt square minus dx square, that is still not for light, this is in general true. Oh, I have to put this term, g22 and nothing else, because only x is non-zero along this path. So dy and dz are 0, which means that, and since this was already a diagonal matrix, there will be no dx dt term. So there is only g22 term, which means that this thing should be equal to c square dt square minus 1. Okay, so you see that I'm taking minus here and then 1 here, and let's say h plus here. It really does not matter. We take a plus h plus cross plus or minus h plus, because both are this is a sinusoidal function, but anyway, let's put it minus. Okay, and we put dx squared. Okay, clear so far? I'm assuming yes. Otherwise, you should do a hand up and ask me or write something on the chat box. Now, I said that this is the path taken by light. So what I can equate this to? I think somebody should write it on the chat box. Otherwise, it is not okay. Somebody has a question. Yes, go ahead.
Hello, sir. Good afternoon. Sir, actually, just a minute back, the video that you showed of the interferometer working.
Yeah.
So actually, from that part, I got a question: is that the interferometers, we build it in the shape of L, right?
Yeah.
There are two arms. Is it possible to build them in the plus formation where there will be 4 laser arms?
Oh, no. Okay, so that is, there can be different configurations of interferometer. We will not get into that direction, but let us focus on this configuration. Okay. I think you can, to see what kind of interferometers are possible and so on, you should see Dr. Sendhil Raja's talk which are there in LIGO India YouTube channel. He describes whole set of interferometers, so you can find it here. But here let us focus on this calculation. So what should be ds square for light? Can somebody type in the chat box? This is the basis of general relativity. So you must have, yes, exactly. This has to be 0. So we can equate this to 0. Now, this is too many things coming up. Then let us do the calculations a little more then. So what we want to calculate is the time light takes to go from the beam splitter, that is this part, to the mirror. Okay, and let's say that the arm length is L. Okay, so the arm length here, let's say, is L. So what should we do? We should integrate x from 0 to L and calculate how much time it took. So the time taken, let's say it is, let's call it tau, is equal to integral dt, which will be equal to 1 by c. I'm just equating this equation. Okay, that you can see that I'm basically equating this to 0 because they are all positive. I can just make it dt, take 1 by c here, and then we have to take a square root of this function, and then dx. So it will be integral square root 1 minus h plus dx 0 to L. Fine. So which would be basically 1 by c integral 0 to L, and then I can expand this as to the leading order h plus by 2. I think you understand this pretty well, dx. So then you will get essentially this essentially is I'll come to that. H plus is a function of both time, space and time, right? But let's say h plus is nearly constant. Okay, that is the key thing here. We'll discuss more about that later on. Let's say h plus is almost a constant. Then what we can write here is this will become 1 minus h plus by 2 by c, and there is this dx, so it will multiply here into L. Okay, that means in general, normally, if there was no gravitational waves, then you can imagine, if I scroll down here, that this length, the time taken to go from here to there by light would be L by c. Instead, it now became slightly different. It became 1 minus this H plus by 2 by C. So sorry about my handwriting with this iPad and so on, because it becomes too complicated, but without writing, I think the whole feel would not come. So then what happened is that this delta tau, for just to go from the beam splitter to the end of the mirror, becomes minus H plus L by 2C. Okay? For the round trip, and this is x direction. Now, if we take the full round trip, then we have to basically take this thing and multiply by 2. So then this is, it is going from the beam splitter to the mirror and coming back. Okay, one side. Then the whole thing becomes minus H plus L by C. Okay, should be pretty straightforward. Now you see, if you now calculate delta Ty, this is exactly the same, right? I mean, you just go there. I hope you can still see the mouse. It's not very clear, but anyway. So in this equation, in the second line, you see this. There was this 1 minus H plus dx square. Now we have to replace dx square by dy square. But the interesting thing that happened is that if you look at this matrix, the 3, 3 item had a minus sign. That means this will have the opposite sign. So everything will be the same, but just that delta Ty will have a sign which is plus H plus L by C. Then the total time difference between the path length, whichever you want to do, delta Ty minus, let's say delta Tx, which will make it positive, would become 2H plus L by C. Okay? And this delta tau is basically like, it's a time difference between the two arm length. So you can interpret it as a length difference. So you can say this is some kind of delta L by C, which would basically imply that the delta L by L is of the order, well, equal to 2H plus. Okay? So that means using this interferometer, we are measuring, we are converting the gravitational wave strain into a strain in an interferometer, that is the arm length, fractional change in arm length. So you know what strain means. In elasticity, you must have seen this, that stress and strain are proportional, and then there is this Young's modulus, etc. So strain basically means fractional change in dimension, which is delta L by L, and as you can see, this interferometer very nicely measures that. But there are many other reasons why an interferometer is important. We will come to that, and also we will come to the fact that why in our calculation we assumed that H plus is almost constant, but then we already integrated over time and so on. How did we do that? So for example, when we are integrating in this equation, integral of dt is equal to 1 by c integral 1 minus H plus, etc. But H plus was a function of time. How could we do that? We'll come to that. Okay, there is a question about in the second last equation, T by C cancels. Actually, I don't know which one is second last because this is not telling me. Can you tell me the equation a little bit? Like second last. So here, the T is here, right? Delta tau is delta L by C, and then here we wrote 2H plus, we equated it with 2H plus L by C. That cancels out. So C cancels out, and then you can just write delta L by L is equal to 2H plus. Okay, I think this is straightforward. There is no problem here. You will see the actual reason. Okay, now I will go back to the slide. Um, so, okay, I have to. There are steps involved. Okay. Okay. So now coming back to this, you saw that delta L by L is equal to 2H plus. That's all you need to know. And this H plus we already showed yesterday is of the order of 10 to the minus 21 or so. It's very, very small. Now, so the whole idea is to somehow amplify that factor. Okay. Second, yeah. Okay. How do we do that? Now, the first attempt to detect gravitational waves was made by Joe Weber. He did not use interferometer. He used just a bar, okay, as shown in this picture. What happens there is that when gravitational waves come, this is a resonant bar, and the frequency of the gravitational waves match the frequency of the bar. The bar goes into a damped harmonic oscillation. It is exactly like when people ring a bell in temples, that it's a damped harmonic oscillation with a strong resonance. So if you could measure that vibration through a system such that the measurement device itself does not induce any vibrations in the bar, that is, the noise is extremely low, then you could measure gravitational waves. But there are several problems with this method. Of course, this effort was extremely important. He is basically the father of, Joe Weber is the father of, let's say, gravitational wave observations in that way. He at least dreamed, I mean, because of his dream, today we have detected gravitational waves. But the thing is that, of course, the first step is always problematic. So there are problems here. The first problem was that what he is, when you have a resonant bar, there is a quality factor, which means that the bandwidth of the resonance is very low. Bandwidth is very low. The quality factor is high. Otherwise, you would miss the signal. The quality factor has to be high so that it can capture the signal. But that also means that only a very few frequencies would be detected by this. So if a gravitational wave is, and you saw in the last lecture that the frequencies of the gravitational waves change with time. It increases with time, at least for the mergers. So only for a brief period in that evolution, the signal is going to stay in the detector band. So then you lose all the signal to noise ratio. So it is a the whole signal, out of the whole signal, only a small part gets captured here. And then there are many other problems. The overall noise in the detectors are high and all kinds of things are there. So this was a good attempt, but it was not enough to detect gravitational waves signals. There were many other efforts later on to enhance the sensitivity by cooling the detector and so on, the cryogenic detectors. The thing is that the Brownian motion in room temperature is so high that the gravitational wave signals becomes much smaller than that. So somehow you have to take care of that part, the Brownian, that you have to reduce noise by some means. The other problem with the bar detector was that it is directional. It could not detect if a wave came, for example, along the axis of the bar. So those are the other problems. So because of which people tried to make detectors which would be sort of like omnidirectional, that it is a spherical detector, so from any directions it could measure the it could measure the gravitational waves and so on. Okay, I don't think we have to get into this anymore. Now let us go to interferometric detector. You must have seen this video, many of you must have seen. So what it does is, I have already explained, I'm just showing the video to sort of load everything in your brain. So the wave comes back through to the beam splitter, they combine. If the interference is destructive, that is both are in the opposite phase, you get a dark fringe. Otherwise, you get a bright fringe. If there is a path length difference because of gravitational waves, which is shown here, then the fringe sort of shifts. And by measuring that, we may be able to measure gravitational waves. That's the idea. And as we showed, that this phase change or the path length difference, meaning the strain in this interferometer is proportional to the gravitational wave signal, which is extremely small. But the question is that how do we amplify this signal? Because if you take a normal laboratory setup, many of you might have done in Michelson interferometry, you know that Michelson interferometer is actually a very sensitive instrument. Without having any ruler in your lab, which can measure like more than say millimeters or of that order, you could easily measure the wavelength of light with a Michelson interferometer. Okay, so this is, you can measure much, you can perform much finer measurements with a Michelson interferometer, but still you cannot go beyond like a nanometer or so. And what we are talking about is a strain signal of 10 to the minus, let's say 23 actually. We need to reach 10 to the minus 23. Even if you take, let's say 4 kilometer detector, so delta L by L is 10 to the minus 23, and L is, let's say 4 kilometers, that is how much? Yeah, let's say 4,000 meters in this thing. So 4,000 meters into 10 to the minus 23 would give you a number which is smaller than 10 to the minus 18 or 19. That is basically smaller than the size of a proton. So that is the kind of measurement effectively we want to do. It is not that exactly we measure that so small distance, but effective measurement, effectively we want to reach that kind of sensitivity. So how do you do that? Oops. Okay, I will come to that. I think that slide is here. Okay, I will go back there later on. So one way to increase the sensitivity would be, the first thing would be that you make a big interferometer. You make it very long, as I said, make it few kilometers long. It's difficult to go beyond few kilometers simply because you cannot get flat land on the earth beyond that. You can go to 10 kilometers maybe, but then even then you have to go underground, otherwise the surface is not flat anymore. Another way is that you take an interferometer, let's say a few kilometers, but that is not enough, but you can do this kind of folding of a light beam. It does improve sensitivity and it can be done, it is done in some labs, but the thing is that is not going to give you enough sensitivity. What is rather done is basically we put a Fabry-Perot cavity inside the arm, Michelson arm. So you see that this is the beam splitter, this is the primary, these are the two end mirrors. Then you put another mirror which is highly reflective here and here. So what happens is that light goes inside. This is not up to the scale. Okay, that this cavity is actually almost 4 kilometers. So light goes inside and then sort of gets trapped. It goes back and forth for like few hundred times and then comes out. So that effectively increases the path length. So let's say if your if light is bouncing, let's say about 300 times, then and the cavity is 4 kilometers, then you get effectively a 1200 kilometer long interferometer already. Then, but even then that is not enough, but I will come to that. Before that, let us understand one important thing. And this is the point which I was saying, that you remember that we consider this H plus to be constant. But then it is actually not, it is varying with time. Then what is happening to our measurement? Let's say you are trying to measure a sinusoidal function. It's a sine of theta. And you want to measure it very accurately. Let's say you want to measure the frequency very accurately. And somebody has told you that if you observe for a long time, then you can get a better measurement. Now, if you really observe a sine function much longer than the period of the function, you would actually end up getting a 0, because it would get averaged out. And the same thing would happen here. Now imagine that a gravitational wave signal is falling on this interferometer, on the plane of this interferometer, like plane of this computer, or whatever device you are watching right now. So what is going to happen is that these arm lengths are going to fluctuate in that picture, like this. That fluctuation has a period, which typically is, let's say, 100 hertz for these black hole markers. So what you have to make sure is that you don't average over a time scale which is more than 1 by 100 hertz. So that is, the averaging should not be more than 10 milliseconds. It must be less than that, so that otherwise you will start messing up the signal. I mean, basically the signal will start getting averaged out and you will not get anything. So that sort of gives you the criteria that what should be the given a length of what should be your effective length of the detector. I think somebody was asking yesterday that what decides the length of the detector. So basically this one would decide the effective length of the detector, that is 4 kilometer times the finesse. Finesse is basically basically the number of times the photon is going back and forth in this cavity. So this effective length should be such that photons do not spend too long, so that it will get averaged out. The signal will get averaged out. So that decides the scale of the size of the interferometer. Okay. Yeah, I remember that I forgot one thing. So I have talked about the H plus polarization, but I did not talk about the H cross polarization, because it is no different from the H plus one except for a 45-degree angle. So if we just rotated our coordinate system by 45 degrees and did the calculation, we would get the same result. So that's why it's basically, there is nothing special about it. Okay, so now essentially you know that we need a big detector, and these are the current detectors in the world. There are 2 LIGO detectors, one in Hanford, it is in the northwest corner, and there is a detector in Louisiana, Livingston, which is in the southeast corner. They are diagonally opposite, sort of, in the United States, and there is a good reason for that. One of them, okay, I'll tell you the reasons right away. One of them is that you want the noise in these detectors to be as uncorrelated as possible. So if you keep them further away, then the chances of correlated noise is less. And the other reason is that if you try to localize a source, if the detectors are further away, then you have a better resolution. You will learn about this in radio astronomy lectures. It's the same idea. Now, there is a 600-meter detector in Germany, in Hanover. That detector, though, has a lesser sensitivity because it is only 600 meter, but I think with folding they actually make it effectively double. But a lot of optics development of lasers and optics happens there, and this is one of the most important places where this research goes on. Then there is a detector in Pisa, Italy, near the Leaning Tower. It is called Vargo. It is 3 kilometers. And all these 3 detectors are online. And there is a new detector which is coming up essentially. It's called Kagra. It is an underground cryogenically cooled detector, 3 kilometers also again. This one has started taking data recently, but then the sensitivity is not yet reached. And then there will be LIGO India. Hopefully, it will start operating in 2025. And I will spend more time on this in the last lecture. Okay. And this is how typically a detector looks. And as you can imagine, 4 kilometers is a lot of, quite a bit of distance. It could be like almost from one side of the city to another side, or let's say center of the city to one side of the city. It's that big. So you cannot see really the end of the detector. This is the Hanford detector in the US, and generally, as you can see, there is nothing around it. And that's a primary criteria for a detector, that there should not be any disturbance near the detector, because the noise created by human beings can be very large. That's one of the limiting factors. So we have to go to a place which is okay. We'll come to that later on. What are the criteria? Okay. Now, so I told you one thing about the design of LIGO, that we basically put this Fabry-Pérot cavity to multiply the arm length, but even then that is not enough. What is done is that, so see, there is let us go through the sort of the design. There is a laser. This laser has to be it's called pre-stabilized laser. It has to have really narrow bandwidth. Then and it has to have only the right modes, basically the TM00 mode, which is Gaussian, and that should go through. The expected power is 125 watt, but it's a huge challenge to get laser power, a continuous laser power with this quality to that level. You can have those metal cutting lasers are more powerful, but this is a continuous power laser with narrow bandwidth. Now that laser comes, I will come to this PR part later on. It goes to the beam splitter, then whatever that interferometer happens, then the light comes out. A lot of light actually comes out of this, and that is like some kind of wastage. But what we can do is that we can put another mirror here. This is called the power recycling mirror, which sees the whole rest of the interferometer as one mirror. And you can resonate the interferometer with this one to make another cavity. So basically, it's a multiple cavity interferometer. And that way, you see that 125, if 125 watt came through here, the power slowly is increased into multiple stages. And in the end, the power in the cavities go to as high as 750 kilowatt, nearly a megawatt. It's an enormous power, right? The power is so large that the mirrors in the end, we are talking about 750 kilowatt of laser power. Okay, it's extremely large. So a continuous power. So the mirrors can actually get distorted. So there are other lasers which are used to keep their curvature in shape, so that the optics works. Okay. All right. Okay. I will break for questions maybe after this slide. So these are the typical parameters of LIGO. The arm length is like 4 kilometer. The cavity finesse is 450. The frequency that is used is 1064 nanometer. The input power could be 125, even though we have not been able to reach the whole power. And there are more things which I will show some pictures and then explain what exactly what is what. But let's stop here with this picture. Okay, anyone has any questions right now? I think it will be better if you raise your hand and then ask the question rather than me reading all this your written. But while you ask the question directly, I'll just try to see what is there. So again, I think now I have explained that why we are assuming H plus to be a constant. H plus is truly not a constant. But what we are trying to do is to do the measurements in very small intervals. Okay, not very small, but it is much smaller than the period of the wave we are trying to measure. And in that period, you can assume the strain to be nearly constant. It is very much like you are trying to, I get the sinusoidal sine wave measurement example. You cannot integrate over all the multiple periods, but if you want to get the frequency right, what you can do is to measure, let's say 2-3. Okay, you can use Nyquist, or you can do little more fine tune to see whether it is really a sine wave or not. But you divide the period, let's say, in 10 parts, and in each of them you make a measurement, assuming that the wave was almost constant in each part, so that you can then connect the dots. I saw a arm was somebody raised hand, and then okay, go ahead. I have unmuted you.
Why we put PR2, PR and PR3? Can we directly send laser on beams?
Sorry, I could not hear you pretty well. Can you please repeat?
Why we put PR2, PRM, PR3? Can we directly send laser on beam slit BSM?
Okay. You are saying that why there are multiple power recycling mirrors, right?
Yeah.
Okay, so I don't know the exact answer to that, but I believe so. What you want to do is to filter out some of the modes. But I can look it up and come back in the next one. I'm not an expert in interferometers, but I can look up that what is exactly is the reason for putting multiple meters.
Okay, thank you.
Any other questions? Okay, there are many actually here, but I suggest, why don't you just ask the question directly? One question is that, does it remain same for H cross term as the strain? It is also the same thing with H plus, just with a phase delay. What is the effect of length of two arms on waves? Well, I think we have already sort of discussed that the length change would be, delta L would be sort of H times L, where H is the strain. From the cavity, how does the light come out? And interferometer okay, so the cavity is not completely sealed. There is a very high reflectivity of the mirror in the cavity, but that means that some part of the light comes out. Why are the gravitational wave observations are in observatories have the same structure? Well, they are actually quite different. The broad structure is the same, but the internal working, internal designs are very the devil is in the details. Actually, they are all different. Two LIGO detectors are basically almost identical, even though there are differences. But the LIGO detectors are by design made to be almost identical, so that when we see the signal, one signal, we see almost the same signal in the other one. Even the exactly same is not possible because of the curvature of the earth and so on, and also the noise level at that point in each place. But that was by design. But the Virgo detector, for example, has a very different seismic isolation, which we will come to. And the Kagra detector is cryogenically cooled and it is underground, so it has a different design altogether. The mirror material is different. They use sapphire, whether LIGO uses fused silica and so on. So there are many differences in the implementation. Okay, I will move forward now. Now, what happens is that with our aim basically is to reduce the noise in the detector so that you can make more and more sensitive measurements. So these are the sort of the noise budget for this LIGO detector. Lower it is better, because then the measurement can be more precise. So there is one more question, that is there any criteria for selecting the location for such a detector? Yes, I will come to that in the last lecture when we talk about LIGO India. So the primary noises are broad, like the broad noises are essentially three. In the lower frequencies here, the noise is primarily dominated by seismic noise. Okay, you can see that there is this seismic wall which primarily dominates. It is pretty high. It is basically determines the lower cutoff frequency, but the overall budget is a sum of many things, and this whole part is actually sort of affected by the seismic noise. Then there is the thermal noise, which controls the sweet spot of the detector. The thermal noise is basically related to the vibrations caused by at room temperature. Okay, this could be vibrations within the strings, those which are hanging the mirror. I'll show you a picture very soon. And the high frequencies, it is determined by the noise is dominated by the photon shot noise, the counting noise in the detector, which is checking what is the intensity of the fringe at a given point. In principle, actually, the LIGO detector does not really do a fringe shift. It is held at resonance through feedback mechanism. Okay, one more thing I wanted to say, and also the thing is that if you increase laser power, this side, the high frequency side actually goes down, the short noise decreases, but then that increases the radiation pressure noise on the mirror, which then comes up at the lower frequencies. So all those things have to be put together in order to design an interferometer. Okay, I will come to that shortly. That how do we come to know about the location of the source of GW? I will come to that. Yeah, I have to speed up here. These are some pictures I will show. This is typically how the LIGO detector looks. Actually, on top of this, there are concrete envelopes in order to protect it. But inside, these are basically, this is the central one is the beam splitter. Then there are these 2 mirrors here and 2 mirrors at the end. These are end test masses. And then one hosts the laser, the other one hosts the detector. This is, so even though here it looks very small, as you can see, these are pretty big as compared to people. The vacuum tube through which the laser goes is about 1.2 meter in diameter. So this is basically how the optics looks. This is the primary mirror, which is about 1 feet, 30 centimeter in diameter. It weighs 40 kilogram. This is pretty heavy. The reason you want to make the mirror heavy is because you have learned in general relativity that from equivalence principle, that the motion of the test masses in gravitational field is independent of their masses. So no matter what mass you use of the mirror, the motion is going to be the same. But heavier it is, it will have, those masses will have lesser acceleration due to other noisy sources like seismic forces or gravity gradient force, that is the other forces of gravity. So basically, and also because of radiation pressure is fixed. So if you increase the mass, the acceleration due to radiation pressure will go down. So that is why the mirrors are made very heavy. But then they have to be freely falling. They have to be floating in the vacuum. So they have to be hung somehow. Okay, and in such a way that it is there almost free. The thing is that the way it is done is that in order to reduce noise, it turns out that you have to use the same material as the mirror, and these are fused silica fibers basically which are used. The same material which makes the mirror is used to make the strings. So essentially this very expensive mirror, which is 40 kilogram, actually hangs by a glass thread. But of course the mirror does not move much. It's very tiny movement, right? We are trying to measure things, the effective distance is less than the size of a proton. So the movement is very small. But during earthquakes, etc., there has to be precaution so that it does not break. And this is how the laser looks like. The laser has to be very stable, and this is the this pre-stabilized laser for LIGO. And this is the optics. And finally, these are the kind of noise we see in the interferometer, and you can see the strain sensitivity on the left hand side. It does touch about 10 to the minus 23. So it is basically to show that it is, at some point it was even Einstein could not believe that this kind of sensitivities can be achieved, and thanks to interferometry we could do that, and many other advancement in technology. So one thing to understand, even if you cannot read this screen, is that to improve sensitivity, when the detector just comes online, the sensitivity is not good, and it takes years of effort to improve the sensitivity slowly. When you reach the final sensitivity, we still have not reached the final design sensitivity of advanced LIGO. It will take some time. So this is the these are the challenges. Many PhDs are involved in just improving the sensitivity or reducing the noise, let's say in a small band. Okay, that would basically mean one PhD. You spend 4 years to figure out that how you can reduce this noise by, let's say, factor of 2 and things like that. This is a log plot, so factor of 2 also does not look too high and things like that. Okay, so yeah, I'm almost near the end of this lecture, so okay, let me see. Okay, so this is Vargo noise curve, that was LIGO and so on. So there, as you can see, since the design is different, their sensitivities are also slightly different. Vargo's target sensitivity is slightly better in the lower frequency, slightly worse in the mid frequencies and things like that. There are reasons for that. The binary spend a lot of time in the lower frequencies during the in-spiral part, so you want to have more sensitivity in the lower part, but that also makes the design of Vargo very complicated. They have a 7-stage pendulum. Okay, so this part about data analysis was quite significant. I mean, I think covered in Sanjit Dhurandar's lecture. Basically, what it means is that in this noisy data, when you try to detect a signal, you need to use the prior knowledge of the signal, which is, and using that technique called match filtering, we do that. So I will basically, okay, maybe I'll just show this thing because many people did not probably understand what match filtering is. So see here, this blue thing is the noise, some simulated noise, and consider that there is this red signal. It is actually a chart signal. It's a very small one, tiny, hidden in the noise. So let's say you don't know where the signal is. So what do you do? But somebody told you the shape of the signal, which is also complicated. It is not that there is only one shape. There are millions of shapes are possible. But let's say you take one, and what you can do, you put the signal here in the second row, and then cross correlate with the noise, with the data, and you see how much cross correlation you get, and you plot it here. Then move it a bit and do the same thing. So when the signal actually matches the correct position, and you can see there will be a peak. So this is sort of like a demo. You see when it comes here, there is a peak, and then if the peak is strong enough, then you can claim a detection. The basic idea of match filtering. Okay, now I will actually skip all those. So basically what is done is that that for every possible mass and spin pairs for the component stars, this model signal is calculated using this post-Newtonian calculation and numerical relativity, and then we do a match filtering with the data and try to find the signal. That is the idea. And okay, so the point is that then even after all this, it took very long time to detect it, and in fact quite significantly long. So the first initial LIGO, which required a lot of effort, was operated for I think 10 years till 2005. At that point, even with all this, the probability of detection was only 2%. That is, we could see a neutron. The probability of seeing a neutron star binary merger was 0.02. That is 2% per year. And the neutron star binary, neutron star black hole and black hole was even smaller. And then see that black hole merger probability is much smaller than the neutron star one. And that is because this is based on our previous knowledge of what we thought about astronomy, how the astronomical sources are distributed and so on. And as you know, things have changed quite a bit. We see much more, many more, like 10 times more at this point. That may not be completely true. Black hole mergers than the neutron star merger. Anyway, so this is the, and then the prediction for the advanced detector, which was almost like 1 per week, like 40 per year and things like that. What is the reason? The reason is that initially the horizon with initial LIGO was, say, something. With advanced LIGO, it becomes 10 times bigger. Okay, this was basically of the order of initially 10 megaparsec and become, let's say, 100 megaparsec. What happens is that if you increase this reach by factor of 10, the distance reach, then the volume increases by a factor of 1000, which makes essentially the probability. So if you see that there was a 2% just 0.02, you multiply by 1000, you straight away get 20. But then the bandwidth, etc., also increase, so you get a larger number. And that will be the, so in the next lecture when we talk about future detectors, so that is the target, that you reduce the increase the sensitivity, reduce the noise level, and try to increase the bandwidth as well. Okay. All right. So now there are many ways how the detectors can be improved. This is advanced LIGO improvement, but this goes beyond advanced LIGO. For the next generation detectors also, this will be the case, like you increase laser power to improve the shot noise. I mean, there are many ways to do it for active seismic isolation, so that the seismic noise can be sort of sensed from the ground, and you feed it back in the signal, etc., etc. But the point is that everything requires a lot of time, and that is what this research is about. Okay, there is one question here. Is there a minimum noise bound by the very nature uncertainty that cannot be reduced in any manner, and how much bound it puts on the detection of gravity? So I don't think there is a fundamental. The question is that, is there a fundamental limit to these noises? Where did it go? Here. The thing is that these plots were actually made using this kind of idealistic situation. So given the noise, the laser power, etc., you try to estimate the noise, but in practice, it is quite far away from that. And I don't know whether, I mean, if you use infinite laser power, well, probably this side, on the right side, will go down, but on the left side, it will come up because of radiation pressure. So there may be some optimization, and then, but it will be difficult to make a frequency independent statement about an absolute limit to the measurement accuracy. But on the other hand, the noise you see in practice, which are like this, are very much different from what actually are plotted there using theoretical calculations. So that limits the main effort of detection. Okay, I think I have to stop somewhere. Let me see what is a good point to stop. So these are now old. That this again shows how the noise is sort of expected to evolve. I will not get there. Okay, fine. I will stop maybe with this one. So finally, with all these gravitational waves were detected, and this is one of those animations which were done by Kip Thorne and his company, and this was also used in the movie Interstellar. So if you have seen the movie, you know that this is the same thing, and essentially by the same people. There may be some differences. So this kind of shows if there is a background galaxy, how it is going to be lensed by the two black holes when they are merging, and then finally it becomes a stable picture. Okay, so I will stop here today and then start in the next lecture with this one, the next detection, because this will also connect to our to the LIGO India detector quite significantly. So I will stop here now and take questions. Let me check if there are questions on YouTube live also. This one. Okay. Okay, I will just go through the YouTube live questions. Meanwhile, and you can raise your hand. So one question is, if a black hole moves in a straight line, can this single black hole system produce gravitational waves? No, it cannot. You need two black holes because the quadrupole moment the second derivative of quadrupole moment is not going to change, even if the first derivative does. So you need to change the second derivative of mass quadrupole moment. Okay. Okay, so I think there are questions here. Check. Right. Yeah. Okay. Second question is how we can neglect the effect of earthquakes in LIGO. We cannot neglect the effect of earthquakes in LIGO. That is a significant challenge. What is done is that, okay, let me go back, show a slide here. See, there are a lot of things, so I cannot cover everything. So LIGO mirrors Earth seismic activities is a major source of noise for LIGO. What is done is that, so now I can show you this way. So many of you actually have done this forced harmonic oscillation problem. And if you see that if you take an approximation, if you solve forced harmonic oscillation, you see this pattern that there is a resonant peak and then there is a tail there. If you go to a frequency which is much longer, much greater than the resonance frequency, you will see that there is a fall off like 1 by f square. So basically, a forced harmonic oscillator, like a hanging pendulum, acts as a noise isolator at higher frequencies. And you can imagine this way. So you take a stone and hang it with a thread, and you hang it slowly. You will see that the stone is sort of moving with your hand. But if you start moving your hand very rapidly, you will see that the stone starts moving much less. So basically, a pendulum is it provides a shock absorbing mechanism. And in LIGO, we use actually 4 stages, and these are the stages. See, 1, 2, 3, 4. So that in order to reduce the seismic effect, and the mirrors hang from this point. Those are also hanging from a stack, and the stack itself has other passive isolation as well as active isolation, where the noise is sensed on the ground and then fed back to the system. Okay, let me check the other question here, and then I will come back. Okay, Aniket Ganguly, does gravity telescopes work on the principle of gravitational waves? I mean, the gravitational wave observatories work on this principle that gravitational waves would create arm length differences in a Michelson interferometer, which can be basically which can be measured with an interferometer. Is there any effect of gravitational waves on the Earth? Yes, there is. The gravitational waves which are falling on the LIGO detectors are creating some strain. Exactly the same strain is produced on the Earth. The thing is that is a negligible effect, however. We can measure it in LIGO because we are amplifying that small signal in multiple ways, removing all the noise, etc. On the Earth, the signal is so small that it will be very difficult to detect it. Okay, now coming back here. Actually, this is like I'm using multiple windows to browse through everything. It's sort of like those musicians who sit with multiple synthesizers. Okay, let me see here. Is the event detection in real time or archival data? It's both. This is a question from Jaswant. Yeah, that's a good question. It's both. What happens is that I will talk about this in the next lecture more. That as soon as you detect a signal, you send an alert to the other telescopes to point their telescopes to the point from which we think a gravitational wave signal has come. So in principle, you want to do it real time. Now, of course, zero time is not possible. So there is a latency, and there is a lot of effort to develop search algorithms which would reduce this latency, and within a minute we should be able to send the message to other observatories so that they can do an electromagnetic follow-up of the signal. However, there can be more signals which are weaker or slightly distorted, or what for whatever reasons did not get detected in the in these online searches. The offline searches can detect more signals, which will be difficult to follow up simply because the event has happened long time, has passed long time. Even because the gravitational waves and electromagnetic waves travel almost at the same time, they may go through. However, that is not completely true for neutron stars, because there, if there is a okay, this may be true for any other sources which can emit electromagnetic waves also, but for black holes with an activity, etc., the probability is low. But anyway, for neutron star mergers, there can be a stage. Okay, I will show that video in the next lecture, where the radio waves, for example, can come like as late as 1 month. So if during this time somebody had performed a search and found that there may be a binary neutron star merger in the archival data, and tells other people that I found something later, they can still point their telescope there and then see if there is something interesting. Okay, another question is that Arjun Dawn, from the gravitational wave, which quantities of the sources that can be stated? Is there anything that can be said about the state of matter? No, matter inside the black holes. What we can, so a black hole, if we believe in general relativity, a black hole is entirely described by its mass and spin, and maybe charge if it is charged. So from whatever observations we do, gravitational waves is probably the only means to do this kind of merger observation. We cannot say anything beyond that for a black hole, because no other information is available. And is there anything that can be said about the state of, okay, and also there is a horizon, so we cannot say anything beyond the horizon. are there any energy losses in gravitational waves or radiation? Can we detect them? So gravitational waves certainly carry energy. If it started interacting with a lot of matter in its path, then maybe it would lose a very small amount of energy, but it would be, I think it will be very, very small. So it will be difficult to detect any energy loss of gravitational waves. Okay, let me see if there are any other questions. Okay, from YouTube Live. Okay. The question is, what is the significance of detecting gravitational waves? Well, there are many many things. Okay, let us first start by asking that what was the significance of Galileo detecting planets with his telescope? So as you can see, that is a very important discovery, and but unfortunately, the importance of science can be realized a little later. So science, of course, for example, Einstein's general relativity is used in every mobile phone and so on. And as you can imagine, that Einstein did not have any clue of that it will be used in mobile phones. So not only how it will be used is not known, where it will be used is also cannot be predicted. In the scientific terms, we have a lot of unanswered questions right now. I will cover this in the next lecture. And gravitational wave observations can help in understanding those. And there are many significant. I mean, we know only a very small part of the universe, even though we think that we know a lot. But when you get into the details, you will see that there are significant, huge questions which are still not known. Like, for example, the Big Bang model strongly must have a phase of cosmic inflation, where almost like fractionally half of the expansion of the universe in log scale happened in that period, and we don't have a direct proof of that. And gravitational waves could be the only proof, only measurement, only possibility to probe that phase, because light cannot come from there. Cosmic microwave background carries an indirect picture of that, and then we do reverse engineering to match that phase. But gravitational waves may be the only direct radiation that is coming out of that, and things like that. Okay, I think that was the last question, and I stop here now. I will talk to you on another day. I forgot when the next lecture.